Okay, so our next presentation, we're moving on now in the direction of handling the data. So we have with us Professor Ross Angel, and Ross, I think you're with the Italian National Research Council now, something like that. So Ross has been doing high pressure research for quite some time and is very expert at this. So please, maybe we can ask Christoph to stop sharing his presentation before you can take over. No problem. Okay, Ross, please take it away.
Okay, so can you see my first title slide?
Yes, indeed. And we can hear you fine.
Thank you very much. Thank you for the opportunity to talk to you today. As Fraser said, I'm now based in Italy at the National Research Council, but 20 years ago, I moved to Virginia Tech in the US, and that's where my connection with Oxford diffraction then was started developed. We founded an X-ray lab at Virginia Tech, and that quite shortly after foundation became the US demo lab. And in actual fact, the original development of high pressure utilities within the Chrysalis software was actually written by the software director, Matthias Meyer, during a series of visits to our labs. And if you want an idea of what high pressure diffraction does to you personally, you may compare the picture on my title slide with my appearance now. That picture was taken in the Virginia Tech lab about 10 years ago. What I want to do today is to summarize a lot of the things that people have already told you in this workshop and discuss their implications for data reduction after you have collected your data. And I feel it's important for you to understand the issues here so that you can optimize your data reduction and improve your refined structures and the precision and accuracy of the structures that you are determining at high pressure. It's potentially complicated by all these issues of diamond cell geometry, diffraction by the diamond cell, absorption by the diamond cell. But with an understanding of the basic principles here, you can then explore how to improve the data reduction beyond the default parameters. For basics, determining structures at high pressure, once you've collected the data, well, even including collecting the data, the workflow is very similar to what you do for surface crystallography for crystal structures in air, maybe at low temperatures. But there are challenges, as we've been hearing. Limited access, absorption by the cell components, low signal because there's a lot of absorption by cell components. Typically, you lose 70% of the intensity compared to a crystal in air due to absorption by the diamonds. There is background scattering sometimes, and you need to maintain hydrostatic conditions so you know what experiment you're doing on your crystal. And most of the implications of these things come into how you handle integration and absorption corrections in Chrysalis. So, as Christoph said, showed quite a few minutes ago, there are different types of basic geometry for the diamond cells, but all of the ones that we currently use for routine measurements at high pressure on laboratory diffractometers have one thing in common, and that is that the X-ray beams, I hope you can see my pointer, but on this lower left picture, the X-ray beams enter the cell from one side and the diffracted beams leave the cell on the other side, and this has become known as a transmission geometry cell. So the beams pass through the cell. This is another example here of a different design, a design built in-house by ETH in Zurich, but basically the same. The other common feature to all of these cells is from the point of view of X-rays, these cells are symmetrical in rotation around the load axis. So the key parameters for making corrections, or the key parameters for determining absorption, are the angles of these beams to the cell axis. And in the good old days, we used to call these psi angles. So you'll hear me referring to them as the psi angles, and there's two of them for every reflection. The angle of the incident beam to the load axis, psi I, and the diffracted beam to the load axis, psi D. As you've seen, the diamond angle cell limits access, so there's a limit to psi max. As I've shown here, this is an even older picture from about 2001. Again, and we got an Oxford diffraction diffractometer. And the maximum opening angle here, which is twice psi max, typically you've been hearing 80, 85 degrees, is limits the maximum 2 theta to which you can measure reflections. So if your full opening angle here is 80 degrees, your psi max is 40, and your 2 theta maximum will be 80 degrees. But that's not the whole story. The access to the diamond cell when represented in reciprocal space is not spherical. It is restricted to a donut shape in reciprocal space. I'll give you the reference to this review paper later, where you can go and read it. What it means is its resolution is very different in different directions, and it's controlled by the orientation of the crystal in the diamond cell. With respect to just total data coverage, here's a little diagram of the total number of reflections from a given crystal as a function of 2 theta, summed up as we go with increasing 2 theta for different wavelengths and different maximum opening angles. And I want to make this point here. Look at the black lines. This line here, you get about 1200 reflections to 80 degrees 2 theta with a maximum opening angle of 40 degrees. If I reduce that to 30 degrees with this crystal, I can only go not only to 60 degrees, not to 80, so I've lost resolution, but I only get about half as many reflections in that 2 theta range. If I reduce the wavelength, go to silver or go to a synchrotron, the number of reflections accessible becomes much greater, as somebody said, Pierre said yesterday, because we're collapsing the diffraction pattern. So the bottom line is with a typical diamond cell with molybdenum radiation in the lab, you will only have approximately 30 to 40% of possible reflections can be measured. So you have a lot fewer reflections than from a crystal in air, which means you're going to be much more sensitive to individual data and failures to correct for things like cell absorption. You have a much higher chance of systematic error, higher influence of random error, and of course you have less resolution. So let's see what we can do to overcome these difficulties. First of all, the thing about diamond cell access. You've already seen several pictures like this. This is an image of a diamond cell frame with some background, and you see it's noisy over here. We've got reflections, we've got background, and on the right-hand side, we've got nothing. And this boundary here is the cut off by the diamond cell, and this is what tells you what psi max is effectively on your detector. I would recommend collecting data to a psi value slightly larger than the claimed psi max or what you think it might be. You will get a little bit more shaded areas of detectors where there's no data or no background. We will have to exclude that during integration, but it gives you some flexibility. And maybe if you're lucky, your opening angle is actually slightly larger than you think it is. So just a couple of words about data collection. It is very important to set the diamond cell exactly face onto the beam when the angles of the diffractometer are 0. Here's a picture done again back, probably best part of 20 years ago, showing how we did it then. Pierre showed you how to do it with the modern instruments. There are several methods to do it. The reason for doing this is it means that all of the corrections are symmetric, more precise, and since the software is based on the assumption that the cell is face on to the beam, the data corrections will be correct. And then you need to collect in what used to be called fixed phi mode. This is a cell being collected with data being collected on a slightly more modern diffractometer, again at Virginia Tech. And you see that the face of this cell, and this is what Chrysalis does for you when you turn on diamond cell mode, is kept vertical. It's much easier to see what this means in Eulerian geometry diffractometers because the plane of the diamond cell is kept parallel to the plane of the chi-circle, and that means keeping phi fixed. That's where it comes from. In Kappa geometry, to get Eulerian phi fixed, you will see that the phi angles actually change from frame to frame in your data collection. But you will see the cell looks like this picture here. Why do we do this? This minimizes the incident angle, the psi angle for the incident beam. It maximizes access to reflections, and it develops close to, results in close to the minimum absorption paths through the cell. So Chrysalis takes care of that for you. Okay, so we've collected the data set, and we've got images like this, where we have an area where we have reflections and background, and we have shaded areas. It is important to set the psi max value, this line here, correctly for integration, not just because there is no data out here, but more importantly, because there is no background out here. And if you use a global background correction, as Chrysalis does, and you include this area of zero background in your global background correction, clearly the background, that will pull the background function down, and clearly the background estimation in the neighborhood of this limiting shaded shade will be wrong. And if you go back in the literature, you will find that's exactly what Brooker software used to do about 20 years ago, and people were wondering why reflections here had the wrong intensities when they were integrated. Chrysalis does this correctly, provided you set this psi max correctly in the data reduction. And Jakob obviously will show you how to do that in the next talk. What you can see here is quite sometimes you get diffuse scattering from the pressure media. Maybe you get scattering from the gasket a little if you haven't centered the crystal very well. So the background in this area which is exposed can be quite structured, maximum and minima, and on the next frame maybe there's nothing at all. So I would always recommend using a combination of local and global background evaluation when doing your integration. And again, Jakob can show you how that is done, and it is easy to turn on and off in the integration part of Chrysalis, so you can compare the two approaches and see which one gives you better data. The last thing you can see in here, this big spot, is not a crystal reflection, but a diamond reflection. The diamonds are single crystals, the diamond apples are single crystals, and they diffract, or can diffract, the X-rays, including onto the detector. In actual fact, there are two types of diamond reflections events. There's diffraction from the diamond, is diffraction from the diamond, but their effect on your data is different. What we've just seen is the red lines are the X-rays passing through the cell and being diffracted by the crystal. In addition, usually the incident beam is diffracted also from one of the diamond apples onto the detector. if that diamond spot ends up where there should be a spot from your crystal, you will have an artificially large intensity for that crystal reflection. You need to exclude that because clearly it will screw up your structure refinement. Chrysalis makes use of the fact that the shapes of the reflections from the diamonds, you'll see on your detectors, they're usually much bigger, but they're different from the shape of the reflections from your crystal. And so there is a switch to turn on what we call profile rejection, and Chrysalis can see that certain reflections do not have the same shape as most of the crystal reflections, and they are then automatically excluded. So they are not there to make a mess of your structure refinement. The second type of diffraction is different and more difficult to detect because it is diffraction away from the detector of incident intensity. So your crystal reflections still have the same size and shape as all the other crystal reflections, but at that point, the crystal wasn't seeing as much incident intensity, or maybe part of the diffracted beam, as I've shown here, was diffracted away, and this reduces the peak intensity. You can't detect these during integration, and you need to reject them when you compare the intensities of symmetry equivalent reflections. So that's done at the averaging step. Okay. So we've dealt with access, and we've dealt with and the importance of dealing with it during integration, and we've dealt with diamond reflections. The last part is absorption. You're all familiar with absorption. It depends on the path length in the material. It depends, so therefore, on the crystal shape and orientation of a crystal with respect to the incident beam and the direction of the diffracted beam. And there's two ways in which you generally correct for it. If you're doing crystals in air, and typically organic crystals with very low absorption coefficients, empirical absorption corrections work very well. But it's also possible, and this was the traditional way of doing it since the 1960s, is you can calculate the path lengths in the crystal and do what is called an analytical absorption correction. So there's two options, and both are available through Chrysalis, and both are available for diamond cells. What I would say, okay, so how bad is the absorption? So here's our cell again, and what I did in this experiment, and if I just want you to look at this bottom set of data, I collected the same reflection by rotating it in such a way that I could change the path of the incident in diffracted beam through the cell. Just to confuse you, for those of you who know about these things, this is called a psi scan. The important point about this is you can see not only is the intensity reduced by 70% compared to the crystal in air, as you change the path of this single reflection through the diamond cell, you change the intensity by about 100%. On this scale, from 120 to 210. So you need to correct for this variation. Fortunately, the primary variables affecting absorption and the path lengths through the diamonds, which are the big effect on absorption, are the psi angles. And as a consequence, empirical scaling in Chrysalis often works quite well and gives you a good start. However, absorption by the diamond cell is often very similar for symmetry equivalent reflections. And it is especially so if you set your crystal in the diamond cell lying on a low index face. As a consequence, the number of equivalents is restricted, and the symmetry equivalent reflections may not give you a good control on what the absorption corrections are. And there's another issue here as well. If you have a crystal that is off-centered, like Pierre's yesterday, I would never collect data on a crystal off-centered. You've seen some excellent examples from Christoph's slides this morning. Put the crystal in the middle of the gasket hole. And if you can't, try again and do it again. The reason being is, if the crystal is off-centered, look at this crystal. Here's a diffractive beam coming from this part of the crystal, passes straight into the diamonds, whereas this one from this edge clips the gasket. So your effective diffracting volume of the crystal is reduced. And of course, if you're doing experiments with much bigger crystals, or you crystallize your crystal under pressure in the gasket hole, gasket shadowing, blocking of the beam by the gasket, becomes significant. It's going to mess up your intensities. Empirical absorption will not work, and you have to use analytical absorption corrections in which you describe the diamond cell, the thickness of the diamonds, the gasket geometry, and so on and so forth. And you can do it in Chrysalis. There's an interface to another program of which I'm not the original writer, but the curator and developer, called Absorb. It's a 60-year-old program, 62 years today, I think. I have to think about that, nearly as old as I am. And Chrysalis will help you interface with Absorb, do these absorption corrections. This is something to try after you've discovered you've got problems, and then follow that by frame scaling. So when you've done frame scaling and averaging, you might think that data reduction is finished. You would just go on to refinement for a crystalline air, but diamond cell data reduction is not perfect. As Christoph mentioned, there's different factors, can be more or less important for different crystals and types of study. And what you need to do after you've got a feel for what's going on with your data is I would encourage you to explore different data reduction strategies, different parameters in data reduction within Chrysalis. And Chrysalis makes it easy for you to do that. Try the empirical absorption first. Find the approach that gives the most consistent set of physically, whoops, sorry, I hit the wrong button, apologies. Gives the most consistent set of physically reasonable refined structures. And what does that mean? Maybe you have to come back and recycle and do a different integration procedure or a different absorption correction and do the refinement again. Why would you want to do this? Well, here's one example. What is my real opening angle, maximum opening angle? As Stas said yesterday, it's often a bit less than you think, not only because of the thickness of the diamonds, but maybe your crystal is off-centered. It's normally off-centered a little bit along the beam. You've got a finite size of the crystal. It may extend out closer to the gasket. You've got the gasket thickness. Maybe you have a small misalignment of the cell. Maybe you've got some beam, that you certainly have some beam divergence, which affects the clipping by the gasket. So how do we find out what's the real value of the opening angle? Well, here's one way to do it, which I described in the reference that I've given there, is you reprocess the data with different values of maximum opening angle. So that's going back right to the beginning of integration, turn off the delete the old background files, delete everything except your data, redo the integration by scratch. It doesn't take long, less time than it takes you to get a cup of coffee. Do all the data reduction steps and have a look at our int. And this is quite often what you see with an integration to 30 degrees or 32, 34, 35 degrees, our int stays down below near to 2%. But look, as soon as I go to 36, 38 or 40 degrees, our int increases rapidly. This indicates there is some restriction to the diamond cell that is interfering with my data in a way that is not being corrected by the standard absorption corrections. And just to make the point, this was the advertised opening angle for this particular make of cell. I'm not saying it was wrong. It may have been that the crystal just wasn't very well centered by me on the diffractometer. But this is a practical way to find out what your opening angle is with your data. So, last few slides, how good are these diamond cell corrections? So here's an example that I did with the collaboration of Almax. I'm very grateful for them loading the cell and sending me a loaded cell to put on a supernova diffractometer a couple of years ago. What we loaded into the cell was a mineral, a silicate. We did the standard data processing in Chrysalis, nothing special. We did some averaging to exclude the outliers and the diamond problems. Our int was 2%. And we did structure refinements. I used the RFine program. R1 from the refinement was just 1.4%. The ESDs on bond lengths are very small. Compared to a data set in air of the same material, the silicon oxygen bond lengths and the metal oxygen bond lengths were correct within the ESDs, but we see a strange range in the ESDs, the uncertainties in these bond lengths. Here they are on a diagram of the thermal ellipsoids of this SiO4 group in the structure. And you can see we've got two small ESDs, same for this one, and a big one here. And what you as chemists can immediately see is we also have a problem with the thermal ellipsoids. This one's a pancake, it's flat. This one's too elongated, and the silicon, which is bonded in all directions, really should be almost spherical. What's going on? These displacement parameters have a problem. You can see it when you do the refinement. We use betas in RFine, but they're like UIJs, apart from a factor. You can see the ESDs in the beta 22s. The U22s are much bigger than in the other directions. And the y-axis of the crystal is along this direction. This bond, which is subparallel to that direction, is got one with the largest uncertainties. And when we analyze the orientation of the crystal in the diamond cell, this is the relative orientation of the diamond cell. So this y-axis was close to the axis of the cell, and you will remember that that means we have very limited resolution along the y direction, and therefore we have very large uncertainties in the refined parameters. As a comparison to prove its resolution and not the absorption corrections that are making a mess to our data, we also collected data from this olivine crystal inside a natural diamond, where we still have absorption challenges. So we corrected for absorption by the diamond, and here you can see spherical ellipsoid for the silicon, and even the RMS displacements of the oxygens with respect to the silicon are slightly larger than the ones from the silicon with respect to the oxygen. So we are getting physically consistent picture even of the thermal ellipsoids. So this is telling us that the high quality structures from inclusions in diamonds, that the absorption corrections are done properly by Chrysalis, and that all the problems we have in diamond cells nowadays are not from the absorption corrections, but this problem with resolution. So just to sum up, I've got a slide with some key points. Some of these are built in. You need to know your orientation of the crystal, the diamond cell, and so on and so forth. You need to do this all on a consistent reference system. You need to keep things simple. Critical is putting the diamond cell face onto the beam when the diffractometer is sitting at 0, and you should do the absorption corrections first, followed by interframe detector scaling afterwards. That sounds a lot of things to worry about, but Chrysalis Pro takes care of all of this. Beyond Chrysalis Pro, to take care of the effects of diamond diffraction and other outliers, you can identify that easily and exclude outliers when you average the reflections and calculate R int. And the critical point is access to the reflections. So plan before you load a crystal in the cell. You can calculate the access and you can figure out what the best orientation of the crystal in the diamond cell is. So having made those points, I will leave my last slide up for a little while, which are a set of references to papers that are specifically written for people beginning diamond cell work, and you should find them quite helpful in designing a successful high pressure experiment on your materials. Thank you very much for your attention.
Thank you very much, Ross. So while this is up, there was just one comment I wanted to make myself again on the alignment of your diamond anvil cell to the phi axis.
Yep.
So you were talking about the effective shading angle or psi angle.
Yep.
If you have not done a good job of aligning your diamond anvil cell body to the phi axis, Chrysalis works on the assumption that that cone shape is symmetrical. And if you've misaligned phi, this will not be symmetrical as Chrysalis sees it. And that means that this side of this shading here will be shaded and this side will not be shaded. So you'll have an effective lower opening angle if you misalign the cell on phi. So I just wanted to add that to what you were already saying.
Absolutely. Thank you. That was a better explanation than I made. If for some reason you collect data that has that problem, you will still have problems in integration. But when it comes to absorption corrections, if you then use the Absorb program, there is a facility in Absorb to take care of that extra cell rotation. If it's desperate, but it's much better to collect perfect data and basically go back and do the data collection again. But I know there's some cases where something funny happens under high pressure and you can't reproduce it. So if that's the only data set that you have, there is the opportunity to correct the data from within Absorb, which is accessible via Chrysalis.
Absolutely. So I hope we can put these slides on the forum so that people can see these links, these references rather. And maybe you can stay around to answer questions after Jakob's talk, since the topics are so closely related.
I will.